Just checking that the audio is okay, so I think we should be right to start. Okay, today I'm going to do a YouTube video on logic gates, and I'm going to demonstrate that with a program called logisim, okay, which is something I've downloaded from the Linux repos. It's a very impressive program. You can do all sorts of circuits. It's very clean and easy to use. I've tried a few before, but I've never found one that's all that great. This one does seem to be a really good, really easy to use, and a really nice program to use. A nice bit of software to use, and I'm going to use it to basically demonstrate how to construct most of the basic gates. So, starting with a Nand gate. Okay, so from a Nand gate, which I've spoken about before in my previous videos, we'll just recap how you can build those from a couple of transistors. So, in this diagram, what the voltage would like to do is flow from VCC to here, but because if both of these are off, okay, then it can't do that, so it flows to F. Okay. If one of them's on, the other's off, it still flows to F, right? Because it can't. This line's broken. However, if both of them are off, then it will not flow to F. It will, in preference, go through to the ground here. Okay. So basically, both off or either one off means F will be on. It's called a Nand gate because clearly it does exactly the opposite of an AND gate. An AND gate, if they're both on, this would be on, and it's sort of one of the basic gates you can start building all of the other gates with. That's why it's important. Okay. So as I say, yeah, from a NAND gate you can build everything else, and literally I think every single gate that you could want to, every single gate you could want to build can be built from a NAND gate. There's some sort of a way of proving that. It's called functional completeness, but I'm not going to talk about that today. You can probably find it on Wikipedia or something. But I am going to talk about how to construct these basic gates here: the NOT, the AND, the OR, the XOR, a MUX and a DMUX. So sort of a lot of the basic useful ones that you would use in circuits. Okay, so let's start with the ones we're going to start with are the NOT, the AND and the OR, because those are quite straightforward, and you should be able to see pretty quickly why an AND gate, a NOT gate is easy to construct, because so a NOT, you just take one input and you output the opposite. So how can you see that that's obvious from here? Well, if you just put your one input to both channels A and B, then if that input's 0, 0 will go to A and B, and the output will be 1. Similarly, if my one input is on, then it will go off. It will never, because it's always coming from the same input, you're never going to have the case where A and B are different. So I'll just demonstrate that with logisim. What you can do is, by default, you normally tend to start looking at main, but main is kind of where you assemble your high level circuit, if you like, and you probably want to construct some lower level circuits first. So I'm going to have this as a new circuit. So I'm going to add circuits. I'm going to call it my NOT. And what do I need? I need a NAND gate, which we'll put on there, and I need one input, and we'll go across from here, and you can see what I'm doing as I go along. These are, you just put your tilted over project as an input. Okay, that's an output. These are the gates. It's quite intuitive. I won't spend too long doing it because you'll sort of pick it up. I won't spend too long explaining how to use logisim because you'll sort of get the logic of it as I do this. Okay, so that's going to go to that. That's going to go to that. And finally we want an output, so we'll drag that over there. This can be used to monitor output, and we'll have the output there. Drag this over to here, it's connected up. And if you want to change the input, so 0 goes to 1, and 1 goes to 0, and you see the NOT gate working as you'd expect there. So that's how you'd do a NOT. Okay, the next probably most obvious one should be how to do a NAND gate, an AND gate, because, well, what would an AND gate be? It would be not an AND gate. So if you take an output from a NAND and put it through a NOT, all of these will go to 0, and that will go to 1. So let's do that next. So let's project, add circuit. It's going to be my AND o.k, and just to show how you can use your own circuits. I'm going to use my knot. So this is effectively the knot that I made, rather than there's a gate for a knot, so you can find it in here, maybe somewhere. Or is it? There you go, knot gate, right at the top. But I'm not going to do that because, well, because I want to show you, I want to show that these things can be built from scratch. So let's go for a Nand gate, and we're going to have a Nand gate. It's going to go here. Inputs goes to the outputs here. Whoops, I don't know if I missed that. Yes, it's gone red because it's not fully connected up yet. Then that can go to there, and I'll do my outputs first this time. And I want my two inputs. Let's input first input there. Can go there. Looks like you can have. I've noticed you can have quite a few inputs, and you can because for a NAND gate you can effectively imagine it quite easily. I would have thought with what would happen if you had more than two inputs. You sort of normally start by thinking about it with two inputs, but it's not difficult to imagine what would happen if you had more. And there we go. That should be something like a NAND gate. Sorry, an AND gate now. So we'd expect 0, 0, it goes to 0. Well, 1, 0 should still go to 0. Other way around should still go to 0. And finally, 1, 1 should go to 1. There you go. So we've set up an AND gate. Now it's again the OR gate is not it's also quite a straightforward one to do. The way you can think about this is, well, this would be an OR, an NAND gate would be an OR gate if I could sort of shift this one down to here. Well, how can I do that? What about if I put A and B in, when they come in, I knot them? What's going to happen then? Well, this certainly will wind up going to here, because if I knot A and B and they're both 0, then I go to 1, 1, and consequently, what would I get? 0, 0 is now going to go to 0, and similarly, 1, 1 would go to 1. Okay, so that would work. Now the knotting so these two have been effectively swapped, and what would happen here? Well, you're just going to, it's pretty obvious you're just going to switch these around, because if A's on, it'll go off. If B's off, it'll go on. You go to this row. So that was effectively that row moved to that row. Okay, it's probably fairly easy to see from the truth table, but it'll probably be easier again to see when I set it up in Flexim. So let's set up an OR gate now. So project, add circuit. I'm going to call this my OR. Okay, and what do I want? I want a NAND gate, which I've already got. I want two NOT gates first of all, so 1, 2 NOT gates, and I want a NAND gate. It's going to go to there. It's going to go to there. It's going to go to output. That's going to connect to there. And I want two inputs. And hopefully, you can see it all goes red until you finally sort of connects an input to an output, and then it kind of sorts itself out where it can. So another input. So you've got two knots. Okay, and there we go. That should now have the functionality of an OR. So, right, well, if I turn that on, that goes on. If I go the other way around, that goes on. And finally, both together, that goes on. That's exactly what you'd expect from an OR. So there you go, we've wired up an OR. So we'll move on to some slightly more complicated circuits and see what we've got. So, okay, now before we do that, you can more or less, just a bit of common sense tells you how to do not the AND and the OR. The XOR is slightly more complicated, so we'll have a look at that. Right. But before we do, just a few things that are quite useful I've found with setting up circuits and things you should be aware of, and you can find them on Wikipedia, no problem, but I'll mention them quickly here. The De Morgan's law, the way I tend to remember it is, if it's not, I remember them together, so if it's not A and B, then you can do not A and not B, but you put an OR in the middle, so you swap this round, alright? So if it was an AND there, it's an OR there, and you see that, okay, so now this one's the same thing really, but it's an OR there and AND there, so following the same logic, whatever it is here, put the different thing there, so if it's an AND here, put an OR there, and vice versa, okay? An OR there and AND there, we switch them around, so OR here, AND there, and we're done, okay? Distributive property, well, if you can multiply out brackets, then You just think of the or here as being a multiplication with maths. You know, if you've done sort of basic maths, you know, to multiply brackets. Just think of the or as being multiplication, the and as being addition, and then your brackets work in the way you'd expect from maths. So the A can go with the B, and the A can go with the C, being ored or multiplying if you're thinking of a maths analogy. And similarly here, if we want to think about how that would work here, just think of the and now as being multiply and the or as being addition, and then the same logic flows through, and you've got a way of working the distributive property through. Now, if you want to prove these things, it's not a big deal. Just and the mainly reason it's not a big deal because there aren't many options that A and B can take because we're doing sort of binary logic here. They're 0 or 1, so proving them is not a big issue. If you want to do that, it's just a matter of a bit of a paper and pen exercise. It'll take you 5 minutes or so. Okay, so next thing then we're going to actually look at the XOR gate. Now, you know what an XOR is as a truth table because well, basically it's like an OR, but when they're both 1, you have a 0, so it's an exclusive OR. We only want to be on when either one of them's on, okay, not when both. It always sort of comes down when people say OR in the English language, what do they mean? Do they mean both, or do they mean just one or the other? Yeah, it's, you know, with logic we've got to be clear about that. A normal OR means both gives you an on, an exclusive OR means both gives you an off, right? So, okay, now how to set up this statement from the truth table is quite interesting because from here you can go to the circuit. So if you just look down the truth table for the outs and you look, well, there's a 1. Well, how do we get that 1? Well, it's not A, but B has to be on. That's how we get a 1 from that one. The other or, so it's got to be both of those things, so it needs to be an and. Or, because that's not the only way we can do it, so we get an or in the middle. Okay, so that there ties in with that line there. Then we have an or, A and not B, right? Gives us the out here as being 1. And those are the only 2 ways you can do it. So that there sets us up for how to do an XOR. So let's go ahead and do that in FlexSim now. So I should need an OR and 2 ANDs. I should already have my own circuit set up for that. Oh, look what I didn't. Oh, I did do that, yeah. So let's go. I thought I hadn't set that up as an individual circuit there. So add circuit. I thought I'd done it in main. My XOR. Okay, and we want 1 OR if I remember right, and 2 ANDs. Let's just double check that. Whoops, don't want to go to that one. Yeah, 1 OR and 2 ANDs. So another AND, okay. If you're not sure what they are, if you hover over the top it'll tell you. And you can change with the presentation, you can I mean, I haven't bothered changing from the default boxes, and it's done the same for the ANDs and the ORs, so it's not good practice, but this is a fairly simple circuit, so it doesn't matter too much. What I would recommend is getting into the habit of labeling these things and changing the boxes as you go ahead, as you go along. It's not difficult to do. Okay, so we've set up our inputs, we've set up our outputs. There's just if you just right click and do presentation. Okay, here, edit circuit appearance. You get various options with which you can change the circuit as you see fit. So let's connect up an output. I don't want to be doing that. Okay, let's connect up our output, so at least that's the most basic part that'll do that. Then okay, I need to have, I'm going to label these inputs now because it's going to get a little more complicated, and just to show you how to do that, I can call that, let's say, A. I can click there, you get a delay there, and I'm going to call that B. Let me get a B there. And what does our first AND gate want to be? Let's flick back and remind ourselves we want to do not A and B, right? So I want to not the A. It's more complicated because I'm going to have another couple of NOT gates if you look there, so I need 2 NOT gates coming in as well. So my NOT, let's shift these things over a little bit as well, give ourselves a bit of room. Give ourselves a bit of room. Move that over a tad. And let's have another my NOT over here. Okay, good. And that could go to there. I think that's gone in, don't know. Not very well, but never mind. That's gone in there. Okay. Now, the first one, let's just remind ourselves one more time, so you probably remembered and I haven't. We're doing not A and B. just navigate around a little bit. So there's the B, and over we go to get the not A. Not A. So that one's not A and B. So this one I would expect is going to be A and not B. So you can always split the signal there. So that's not B, and we also want it to be A. So let's drag that down across. We don't want it to join, so let's make sure we go over the top there. See, there's no knuckle there, so it hasn't. There's no little round dot, so it hasn't joined them up. Keep going down and over, and I think that should now be the circuit done. It's all connected up, so there's no red bits. So that's A. So that's going into this AND here is not A and B. Going into this one is A and not B. So it's zigzagging down there with the A. So let's see if it works. So 0, 0 gives us what we want. 0. That gives us a 1. Let's start the other way around. That gives us a 1. Good. And when they're both 1, we should get back to a 0, and we do. So there you go. You got an XOR done. Now the next two circuits I didn't come across until background in programming, but I'd never come across a mux and a demux until I started messing around with circuits. So we'll talk about what they do first, because if you're anything like me, you won't know, or at least you won't know to begin with. So the idea of a mux is that you can select whatever input you want. So you've got these two inputs A and B, and you want to send one of them to an out. So if you set S to be 0, you want the A to go to an out, whatever it is. If you set S to be 1, you want the B to go to the out, whatever B happens to be. So when S is 0, the out should follow A, and that's how I've set up my truth table, irrespective of what B is. Doesn't really matter. Okay. Similarly, if S is 1, my input A is, then I want my output to follow B. Sorry, don't I? So here doesn't matter what A is, so we get B in. And if I do the same thing, it's just to show you how the distributive law can make things a lot simpler. And just notice I've missed an AND there, which I'll tell you about in just a moment. Okay. Well, if we look down here, then and I've just done these two, and that's a long statement just for these two, but it does make sense, because what are we doing? Not S and A, and not B. That's one. Okay, not S and A and B. That's the other one. So either all of those, so and all of those, or all of those. Okay, that's quite a long statement, but if you notice that this part of the statement, the not S and A, appears in both, so you can use your distributive law to take it outside, and you should put an AND here. Okay, so there's an AND gate missing there, but then that means that you've got not S and not A or B, because those are the bits that are left over. Well, not B or A is clearly going to be 1, right? Because of logic. Okay, if B's 1, well, that'll be 0, but that's fine. But if that's 0, then you're going to have a 0 and a 1 here, are they? Either way, you switch B, so that's fine. That means that the OR is always going to be on. Yeah, so the output of this statement here is always going to be true, so you don't need it. So this is going to come down to, this whole statement here, using the distributive law, is going to come down to not S and A. And that's that done. Apart from, you see, I've only done those two rows. Obviously, I need to do these two as well. But using a similar sort of idea, and you can see it from the table as well, because the output follows A, so it doesn't matter about B. So you can kind of ignore it. So you can just do not S and A. Right? That's when it needs to be on. Or S and B. Right? That's the other way. And it's, again, this is the one that looks, actually, when you set it up as a circuit, actually, it's kind of more obvious how it works. It's always good to have different ways of looking at circuits. I've noticed as I've started doing this, because some ways, I think this is so obvious. Well, it is obvious, but once you see it as a circuit, it's kind of a level more obvious again. Okay, so let's go to logisim now. I've set my mux up earlier on, so let's have a look at that. So I can do edit circuit layout, and that'll bring that circuit up. What I've done is I've put them both onto a clock, and I've put this, the A here is going to go up and down with 1 click. The B is going to go up and down with 5 clicks. So what should happen, just so you can see how the output follows the different inputs more easily, because if I now simulate the circuit, I enable the tick enabled, right? You can see that at the moment, what's it doing? It's following the A. You can quite clearly see that. It doesn't matter what B does. Okay, everything along here is just following the A right up until the very end, until I change the S, And now what's happening? The A is going on and off, doesn't really seem to do anything. However, every time the B changes, wait for it, there you go. The output changes, so you can see the output's now following B. Okay, which is exactly what we want. Yeah, and you can kind of see that. Well, what's the effect of this S? Well, when S is 1, it gets knotted and it stops. You can think of it stops the output from here. It just goes to 0. So everything that comes into the OR is going to come from here. The OR is going to be sort of driven, if you like, by this signal. And vice versa, if I changed the output to 0, this will now be blocked, right? This will be on, and everything that the OR does that comes out of the OR is going to be driven by effectively this signal here. So in many ways, a mux is, I think, easier to understand when you look at the diagram like this, particularly when you can simulate it. It makes it sort of adds another level of understanding to it, doesn't it? So that's the mux. The next one we're going to look at is the demux. So let's just try and understand that. Now, there wouldn't really be too many prizes for guessing what a demux is going to do once you've understood a mux. So let's click on. So what happens when S is 0? It goes to A. When S is, yeah, so a mux, just show how clearly they're opposites. This takes 2 inputs and goes to 1 output, right? And you can select between the inputs. So this means you take 1 input and you can select between the outputs, okay? And it's actually sort of simpler to see what's going on. You've got 2 outputs, which is a bit different here. You've got A and B. I don't think we've had any other circuits with 2 outputs before, but other than that, not much difficulties going on, and really it's quite easy to program because, well, when's A on? It's when S is not on and in is, right? And when's B on? Well, it's when S and in are both on. So it's very easy to see how the logic's set up here. And let's just go to logisim and see these two in action. Okay, so let's edit circuit layout. That brings us to this one. So what I should see with this one is a little bit different. I should see that when I put S is 0, A is following this input, and that's what's happening at the moment. It's going on off with A. So the input here is going to A, and this just outputs 0. Okay, if I switch it round, what's going to happen? The signal's going to go to B. Okay, so I hope you enjoyed the video. Thanks for watching. As I say, I've got lots of other videos in my list all about sort of low-level computer, low-level ideas about how a computer works. I'm going to do one on SR flip-flops, hopefully next. So keep watching, and do check out the others in my list. I've noticed one of them seems to be very popular, and others aren't getting watched at all. So I hope they're all about the same sort of standards. So please check out the other ones as well. Thank you. Bye.